Now, so very good, right? So now you know how to save the, how to change the parameter file. Now you understand for S device, we have input file. One is the command and other is the parameter. That is what you can change. Okay. Now let's, now I'm not going to do hands-on, right? We're going to copy from somewhere. Can you go to the getting started as device? Am I looking at CMOS inverter? Double click it, copy to your home directory. Double click it so that we are in this directory. And I would like you to first see you might not have changed the job, local maximum job yet. Go to edit, preferences, right? Make the local job, maximum local job to 4. I think to end you already have that. If right. Okay, can you do that? When you're done, when you have copied it, everything all right, please let me know.
Okay.
And you can go ahead to submit the job to run. Just run the project. Explain what this project is about, right? It's not difficult. What can I do? I can either look at the command. Then I know what it is talking about, right? I know it is what, but I see there are 2 SDE. Let me open up both of them at the same time, right? I'm not going to read the command. I just open them. The final result. Open into the same as visual, right? If you remember, what I can do is also I can Control A, select both of them, and then link them. But what I see clearly is one of them has red color in the source string, and other has blue color in the source string. Remember what is the meaning of red or positive number? Is it N type or P type? Huh?
I think it was N type.
N type, yeah. So basically on the left is a NMOS, N, P, N. Okay, right is a PMOS, N, P, N. So basically based on this, you know that, okay, it generated 2 structure. One is NMOS, one is PMOS. Of course, they all have their contact. If you scroll down, they all have substrate, gate, source, and drain, right? I won't go into details. Of course, you can, again, like what I said last time, turn off everything, and then just try to inspect which one is gate. Top is the gate, which one is drain. Drain is on the right, which one is source, and which one is substrate. Just make sure everything makes sense, right? People create substrate, they don't want to really mess you up, call this gate, although in principle it still works as long as you apply the right word function. It's just a name. But however, usually they will do it in the traditional way. So everything looks right. N1 is NMOS, N2 is PMOS. Okay. Now, then I look at these 2 SDYs. What are they? This one I really need to do a right click, edit, look at the command file. Wow, look at this. A little bit DC, but we understand some of them already. Electro session, yeah, source, drain, gate, substrate. File telling me where to read the structure. This is something I don't understand. TDR/NMOS. So this is another built-in variable. It means you take the TDR under the NMOS label. This one I have not taught you. If you go to view, table option, you say show tooth labels. You find that every tooth has a label. Remember when you try to create a new tooth, for example here, you actually can put label also. Usually we don't put anything, we just use the default. For example, I try to have the S device, right? Let's say S visual. it just put as visual as the label. I can change it to my, for example, extract VT. Then it becomes a label. Okay, I'm not going to use it. I just cancel. So every truth has a label. Basically, now last time I said if you put TDR, it's going to take the last, the nearest truth that can generate the structure for it to use. Then it's going to take this one. But no, this one I want to take the NMOS first. That's why we say TDR vertical bar NMOS. Then you know that you need to look at this node. Similarly, it also have TDR PMOS. Now you see that there's some difference between what we have learned and here. It has a higher level called device NMOS. NMOS is just a name. Device is the keyword. Basically, say that, hey, I'm going to use a device. What device? I call it NMOS, any name, my NMOS. But this device, you need to find from here. It also has this physics, and it has this electron. So basically here, I call two TCAD devices, NMOS and PMOS. I have not told you how to do simulation yet, but here it's just saying that basically it's like in the EE124 lab, you told your partner, give me a LM741 like this. And maybe I should not say that. Just give me a NPN or a NMOS. I forgot the model. Give me a NMOS and give me a PMOS. I need to do some experiment. But what NMOS do you want? Okay, this file. It's just like that. Okay, this model mentioned in the menu. And here, which PMOS? This model mentioned in the menu. And this PMOS has 4 electrons. This NMOS has 4 electrons, right? But this is a simulator. You also say what mobility, what model you want to turn on. Okay, so now you get these two devices and you have not done anything. Is this clear? Any questions?
Yeah, that's clear. Do you want us to visualize everything?
And maybe not yet. I want to explain first and then you visualize those devices.
Okay.
Okay, right. So your partner give you two devices, NMOS and PMOS. So I actually forgot what is the goal here. Maybe you want to connect them together and build an inverter. I want to put V in and measure V out. Hey, this is very familiar to you when you use LT spice, right? Or other spice. You just get the NMOS, a model, dot model, NMOS, and then got dot models PMOS. I did not really do it well. And then we build the circuit to connect them together and do the simulation. This is called spice simulation. In LT spice, most of you only work with the graphical interface. But actually, they all convert this graphical interface into a so-called netlist. A netlist tells you how each terminal are connected to each other, and then it runs the simulation. Okay, have you used any netlist before?
No, I haven't.
You haven't, right? Tuyen, did you have chance to use netlist?
No.
No, okay. So so this one is that usually if you are a graduate student, you would have played with netlist. But so now the teaching will be opposite. Usually I would just say that this is just like your HSpice netlist. Now let me just tell you what's going on and then we can continue to discuss. We then have something called system. This is basically telling the netlist. And what we are doing here is called mixed mode simulation. So what does it mean? First of all, it says that I have a model called voltage source. You see, very similar to your LT spice. It has two nodes. One node is DD, one node is 0, and you start with voltage equal to 0. This statement is just the same as in LT spice. You drag the voltage source and then you connect it with a ground and you set the voltage equal to 0. Okay. I also have another voltage source. Okay. And by the way, I give you the name called VDD. Second voltage source, the name is called Vin. How do you connect it? It has a node called in, another node connect to ground. I also start with 0 volt. Okay. And then I say, I have a transistor called NMOS. Don't worry, what transistor is this? But I told you earlier, this transistor come from here, okay, NMOS. So give me an NMOS. Which one? That NMOS, okay? And I call it NMOS 1. But which transistor? That capital NMOS. Where do I find it? I already specified in the device NMOS. Use that TDR. Just like in the lab, you tell, or in your LT SPICE, you say, I pick this model as the NMOS. How do I connect it? Well, it has a terminal called source. Connect it to ground, please. It has a terminal called drain. Connect it to out. It has a terminal called gate. Connect it to in. And it has a terminal called substrate. Connect it to ground. Just like what I'm drawing here. Right? So here you don't have a SPICE model because you invented a new transistor. No one else in this world know about it. You have not characterized it. You use TCAD because it solves the Poisson and continuity equation. It can predict how the transistor works. So you just use TCAD to do the simulation for this part. And now I connect this one. Again, I say, give me another transistor, PMOS. I already told you where to find it in the device PMOS. I call it PMOS 1. Again, where is the source? Connect it to DD. Oh, DD, isn't that we already have a DD? How about the drain? Connect it to out. Oh, we already have out. That means it's connected to the drain of the NMOS. It also have a gate, connect it to in. Oh, I already have the in, right? And then you have a substrate, connect it to DD also. Now, after this connection, I think you already see that this is nothing but just an inverter, right? This is the voltage supply, this is the input, and this is out. And besides that, I also drag a capacitor. Okay, how do I connect it? I say connect it to between out and 0. I'm right. And what is the value? 3e minus 14 farad. Okay, so I finish the connection. And then I say, okay, solve this circuit. Now, this is not just a SPICE circuit, because at the same time, I need to solve all the Poisson electron hole equation inside this device. So it's a very complicated, right? If for SPICE, you only solve the circuit, KCL, KVL. Here, you solve also for Poisson, electron, and hole continuity equation. Okay? And I say, you need to save the time. This just take it for granted. You won't be able to memorize. I want to save this node value, V in, V out value. The current going into NMOS 1 to out. The current going into PMOS 1 to out. And also the current going into the C out. So is this okay for this system session? Do you know what I'm talking? Any questions?
I think that was clear.
Okay, very good. Yeah. You're okay, Tuyen?
Yeah.
Okay, good. Yeah. Just know about this. In the future, you will see new thing. Of course, you need to sit down and draw it carefully. But at least you know that we can have something called mixed mode. Why it is called mixed mode? Because if you are a circuit guy, you always just use solve the KCL, KVL. And this one is a compact model. It's a SPICE model, very simple model. We tell you that if you apply a gate voltage and that drain voltage, how much current you will get. But here, we don't know the relationship. We know the relationship by solving the Poisson electron hole at the same time. Okay, it is just like you are super fast, and then your labmate is solving the circuit equation. He will ask you, hey, I'm applying 5 volts to the gates and 0.1 volt to the drain. What current will go up? Then you measure your device immediately and give him the result or her the result, and then you solve it. And then he go to another voltage and ask again. Okay, so this is called mixed mode. So it has both TCAD and SPICE. Now, so the rest is just math, plot, you know already. Just the most important is that we have an extra session. You need to define a device, right? After this, you go to solve again. And this one should be trivial to you now. Start with Poisson. Solve all the circuit and contact equation. And then I do quasi-stationary. Here, look at this. I'm ramping the SPICE parameter. Okay, so don't worry about why it is not go, right? Because this is just a template. But you know that what it tries to do is that we start with VDD here. Where's that? We start with 0. So I want to ramp VD to 1.5 volt. I want to bias my inverter to 1.5 volt first. Okay, so that is quasi-stationary. And then what do I do? After this, I change my input voltage to 1.5. Okay, so I'm going to look at the output, right click, visualize file. There are many files, but what I'm going to read is the system file, right? Because for this system, it is saved as this. Remember what is at node? It means the current node. That's why it's substitute with free and free underscore sys.ds.plt. I open it. And then I try to look at the V in as x-axis, V out for y-axis, and then I get the typical VTC I got as an inverter. I can also plot the current going through the NMOS. I plot it to the right, so because they have different scale. You see that when they're switching, of course, there will be a lot of switching current, and then go back. Okay. So basically, that's what I want to say, right? So, and then the last one is a switching. This is not too difficult either. Again, start with the device. Also have the same circuit, but this time it add a pulse. This is a pulse you also can find in LT SPICE. And basically what it say is this. I have two values, start with 0 and then go to 1.5. Well, please delay for 10 picosecond and then go to 1.5 at 10 picosecond. The on period is 60 picosecond and then go down with 10 picosecond. Okay. And then the total time is 140 picosecond and repeat. Okay, this pulse is also in the SPICE. If you're familiar with the SPICE, this is what it has, right? But not very important. Again, you don't need to memorize. The point is, after this, what do I do? Again, I ramp up the VDD to 1.5 volt. And then I do a transient simulation. I say that I want to go from 0 to 200 picosecond. I plot it. Okay, so the last task for this class is take a look at this file. I want you to plot the input voltage as a function of time and also output voltage as a function of time for the last switching. Okay, try that and let me know if you have any questions. Look like, right? So let me also plot it since you plotted already. I right click it, right? So what I'm going to do is look at this system file. I look at Vin. I will plot the time in the x-axis and try to make sure that, so sometimes you might set it wrong. So the best is to look at what it looks like, right? So I see that it goes up, go down. And I look at V out, I will see this type of slope because it will charge the capacitor, discharge the capacitor, right? And it also has overshoot.